Hi folks, welcome to part 1 of Unit 7, Lesson 4. So here we have the diagrams, a quick recap of the 8 scenarios we can have when we're considering 3 planes in R3. So you notice here that I've grouped them in particular ways. So I've grouped 1 to 5 here are all the scenarios where we have um, at least 2 parallel planes. Okay, some parallel and coincident, some parallel and distinct. And the reason why I group these together is you should be able to work with these scenarios without having to do much algebra, because you can tell when planes are parallel. You can also distinguish between parallel and distinct and parallel and the same. And then you know that if you have 2 parallel planes, the third will clearly not be parallel, and then you can determine, based on whether 2 of them are distinct or 2 of them are the same, whether you're going to have an intersection in a line like here or no intersection at all. So these are all things that can be easily determined, or at least the nature of these intersections be determined by looking at the normal vectors and which ones are parallel. So my focus now in number 2 is going to be on these here. Okay, so here notice is how I'm able to draw a cross section of 3 planes, and you have to think these planes are coming out of the paper. So here in pairs they intersect in a line, but there's no intersection between all 3 planes, as opposed to number 7 where all 3 intersect in the same line. And then we've got this one apart. It's the only one where there's a single point of intersection. Okay, you notice here how I'm not able to draw um, a cross section of this. I have to try to show the depth to show that it's got this one point of intersection. So I'm actually going to show it with some cardboard later on. And we want to see if we can distinguish between these 2 scenarios and this scenario where we have only one solution. The reason why we want to do that is often we're only interested in systems of equations that have a unique solution. So if we can eliminate the possibility that there's going to be either infinitely many or no solution based on numbers 6 and 7, uh, to determine before we start doing the fairly heavy algebra we're going to have to do to solve these questions, to figure out, yes, I will indeed have one and only one solution. Okay, so this is what we're going to talk about here. And as we talked about the normal vectors when we were talking about the parallel planes, hopefully we can make some sort of determination based on the normal vectors of the 3 planes in cases 6, 7, and 8. Okay, so I'm just going to move this up a bit here because I want to actually look at my 3 scenarios. So the first one I'm going to look at is the triangular prism. So I think you can sort of see it. Okay, and if you look here, if I take a cross section, okay, there we go. If I take a cross section, it's just going to look like a triangle. Okay, but what I want to do is I want to look at these normal vectors. If I take a normal vector to this plane, and then say a normal vector to that plane, and a normal vector to this plane, okay, there's something special about what I'm able to do. Because I'm able to draw this cross section, I can put the normal vectors all along the same plane. In other words, these 3 vectors are coplanar. They can all be drawn on the same plane. Let's see if the same thing can be said of the other 2 scenarios. So the next scenario I'm going to look at is the sort of the asterisk or the star, okay, where all 3 planes intersect in this line. And I see here that I can draw a cross section, okay? And let's see if these vectors are coplanar. Well, there's one vector, second normal vector, third normal vector, and I realize that I can draw these vectors all along the same plane. So they're coplanar. Whereas when I take the third scenario, the one that I'm really interested in distinguishing, so here if you look, you see that you've got a single point of intersection there. Well, if I take the normal vector to this plane and the normal vector to that plane, they possibly could be coplanar, but then the normal vector to this one here, there's no way that this one can lie on the same plane as the other 2. Now, why is that important? Well, because first of all, it distinguishes the scenario we're interested in, the one with a single solution, uh, from the other 2 scenarios. And secondly, it's interesting because we already have a way to determine when vectors or three vectors are coplanar. Okay, something we talked about a little earlier on. So let's come back here, bring this down a little. Okay, and let's take a look at our three scenarios. So if we take our scenario of the triangular prism, we see that again, because I can draw the cross section, it means that I can draw the three normal vectors all along the same plane. Okay, how do I know I can do it? Well, I just did it. Okay, same thing with the star or the asterisk. Okay, 1, 2, and 3. They can all be drawn along the same plane. Okay, but we saw a little earlier on that there's a very easy way to determine whether three vectors are coplanar. We just have to look at the scalar triple product. So if I take the triple product n1 dot n2 cross n3, okay, remember, first you have to do the cross product, then the dot product. If this is equal to 0, so if this occur, then normal vectors are coplanar. Okay, and what does that mean? So again, we're assuming here that we've already determined that we're not looking at parallel planes, that if this triple product is 0, it means the normal vectors are coplanar. That means we have either option 6 or option 7. There's no way for these three planes to intersect in a point. Whereas if n1 dot n2 cross n3 is not equal to 0, then the vectors are not coplanar. And what does that mean? This implies that there is a unique point of intersection. Okay, so before starting a problem, you might want to check the scalar triple product, and if it's equal to 0, then you know that you can't have a single solution. Now, the problem here is that there's no easy way to distinguish which one of these it will be. So if you really do need to know the geometric interpretation, you will have to go ahead and solve the problem, which is what we're going to see how to do a little later on. Okay, but if you know that the triple scalar product or scalar triple product is not equal to 0, you can be guaranteed of a unique point of intersection. All right, so what I'd like you to do now is work on number 3. Okay, it'll take a second for, there we go. Work on number 3, and notice here that I'm just asking you for the nature of the intersection of these three planes. So I'm not asking you to determine what the intersection is, but based on whether there's parallel planes and based now on the scalar triple product, you should be able to tell me what the possibilities are. So in most cases, you should be able to tell me exactly what's going on, although there might be some cases where you can give me only options. Okay, so work on this and we'll come back together and take it up together.